Welcome back to the deep dive. Okay, today we're taking a bit of a hard left turn, actually, away
Yeah.
from the usual transformer models, the
Huh?
ones grabbing all the headlines.
Right, they do dominate the conversation.
Exactly. We're diving deep into the incredible resurgence of recurrent large language models, specifically the RWKV architecture.
A really fascinating space right now.
It is. And our sources today, they're pulled straight from a pretty pivotal research paper. It proposes this framework they're calling DREAMSTATE.
Mm-hmm.
And our mission here is, let's say, pure scholarly interpretation. We want to understand how researchers are fundamentally rethinking knowledge representation inside these efficient
That's
RNNs.
a big shift in thinking,
Totally. Treating their internal state not just as some temporary output,
like a passive memory dump.
right, but as a truly editable generative knowledge object. That's the core idea.
And that premise, that's what makes this research so exciting, I think. I mean, for years, transformers seemed kind of unbeatable, right?
Yeah, that was the narrative.
Mostly because of that attention mechanism, handling long-range dependencies. But modern RNNs, like RWKV,
Which stands for Reinforcing RNNs for the Transformer era, for those keeping track.
exactly, they offer this incredible linear time inference efficiency, much faster for generation, potentially.
But they always had that Achilles heel.
The state management, yeah. Robust state maintenance over really long sequences, that was the struggle.
So what changed? What's the breakthrough here?
Well, the breakthrough that really motivates this paper is a deeper understanding of the RWKV state mechanism itself. It gets a bit technical, but...
Go for it. Our listeners can handle it.
Okay. So historically, one reason some older linear RNNs just failed at complex tasks, think logic puzzles or tracking parity in code,
Right, things needing robust memory.
was a mathematical constraint. The eigenvalues of their state transition matrix,
Right.
they were stuck between 0 and 1, $0, $1.
Eigenvalues. Okay, break that down conceptually. What does that range limit actually mean for the model's memory?
Think of it like this. Constraining it to $0 basically meant the model could only manage memory by, like, adding positive information to the state.
Reinforcing things.
Exactly. Or just letting it passively decay towards 0. It was only positive reinforcing memory. But by extending that range to include negative values, so from -1 to 1, 1 a lover, 1 a loller,
Which newer models like RWKV7 goose leverage?
precisely, you fundamentally unlock the ability to manage decay actively, or forgetting, or even reversals in logical tracking. You can subtract or negate influence.
Ah, okay. So it's not just adding or fading, it's active management.
Right. It makes the RWKV state provably more expressive, more robust than those older fixed-range architectures.
Okay, let's unpack this. So the memory state, it's gone from being like a simple bucket to something structured, powerful, dynamic. And if the state is suddenly this rich, well, the logical next step is to ask.
Can we do something with it?
Exactly. Can we actually map it, navigate it, manipulate it like a, meaningful vector space?
And that question leads us straight into their first big idea.
Which brings us immediately to segment 1, mapping the internal state manifold with dream state. The researchers basically said, okay, if this RNN state is so expressive,
We should be able to model it, right, generatively.
and how did they approach that?
Well, they brought in a technique that's become super familiar, especially in the creative AI world. Diffusion models.
Ah, diffusion, like generating images from noise.
Exactly, that core idea. Specifically, they used a conditional diffusion transformer, a DDIT, built on the standard denoising diffusion probabilistic models framework, DDPM.
So for listeners maybe only familiar with diffusion for, say, scalable diffusion making pictures, we're talking about using that same powerful noise-to-signal process,
Yep.
but applying it here to these like massive high-dimensional state vectors that represent a way of thinking, not a visual scene.
Precisely. They learned the probability manifold of the state, basically PPSC. This lets them generate or even edit a state dollars based on some context.
And this does what for their argument?
It validates their whole foundational premise. It shows the high-dimensional RWKV state is, and I quote, a well-defined object for generative modeling, just like an image or audio.
Okay, so they can model it, but the proof is in the pudding, right?
Yeah.
How did they demonstrate this actually works in a meaningful way?
The proof of concept is actually pretty elegant, I think. They ran this experiment generating states from a whole bunch of different prompts.
What kind of prompts?
Each one defined a specific expert persona. Things like act as a Linux terminal or act as a storyteller, act as an Ethereum developer. a diverse set.
Okay, so different conceptual roles.
Right. Then they took the actual state vectors generated by the model for each persona. And these things are huge, remember?
High dimensional.
Very. And they projected them down into 2 dimensions using TSNE visualization, just to see if there was any structure.
Yeah.
The result was genuinely striking. When you plot those 2D points, the states formed these distinct, really meaningful clusters.
Clusters based on the persona.
Exactly. All the technical personas, the coders, the systems admins, they clumped tightly together in one area of this conceptual map.
And separate from.
Totally separate from the creative personas, like the storytellers and poets, which form their own cluster elsewhere.
Wow. So it's not just some random internal mush. It's literally a map of concepts.
That's the key takeaway. It's crucial empirical evidence that this RWKV internal state isn't just noise, it's a structured manifold. It actually encodes high-level concepts and operational modes.
And why should you, the listener, care about this? What are the implications?
Well, this isn't just a pretty picture for a research paper, right? It has potentially massive engineering implications.
What?
Think about it. Maybe we can replace traditional prompt prefixing, feeding the model a long text instruction at the start.
Which costs tokens, costs compute time during inference.
Exactly. Instead, you could potentially just do a zero-cost vector injection. Pass in one of these generated state vectors.
And instantly change the model's entire conceptual framework, its persona.
That's the idea. Huge potential efficiency gains for complex, multi-step workflows where you need the model to switch roles or topics quickly.
Okay, so we have this map, this structured manifold. The real trick then becomes navigation, right? How do they prove they can actually use this map to steer the model with precision?
Which leads us perfectly into segment 2, this idea of unprecedented conceptual control via state interpolation.
All right, what was the setup here?
They set a pretty tough task for the model. They wanted to prime it to act specifically as a storyteller,
Okay.
but on the specific theme of perseverance, not just any story.
A targeted creative task. How did the baseline do?
Well, when they just used a generic state, the baseline model basically failed. It just produced some generic meta-commentary about storytelling. No actual story, no perseverance.
And the first dream state attempt, just generating the storyteller state.
Better, but not perfect. It successfully adopted the storyteller style. The voice was right.
But it missed the topic.
Yeah, it kind of wandered off, didn't really hit the perseverance themes specifically.
Okay, so this leads to the really clever part, the interpolated state. This sounds like the aha moment.
It really is. Instead of trying desperately to generate one single perfect vector for storyteller who talks about perseverance.
Which might be hard to pin down.
Right. They leveraged the generative nature of the diffusion process itself. They played with the noise vectors used to generate the states.
How so?
They generated 2 different states. State A, targeting the concept story on perseverance, and State B, targeting a different concept, story about a desert-facing climate change.
Okay, 2 distinct ideas.
Then they created a hybrid state by essentially blending the noise vectors that were used to create State A and State B during the diffusion sampling.
So interpolating in the latent noise space, not the final state space.
Exactly. And then they initialized the RWKV model with that hybrid state.
And the result?
For the resulting text was this truly seamless blend. It generated this really creative metaphorical narrative.
The quote you mentioned earlier.
Yeah, the one about, if you look at the desert as a painting, it's been exposed to many storms and droughts. We must change the deserts we live in. It perfectly captured perseverance through the desert metaphor.
Wow. That is impressive. It's like mixing 2 specific primary colors on a palette, right?
Like analogy.
You take the abstract concept, perseverance, and the concrete image, desert, and you blend them to get this third, complex, metaphorical shade.
Instead of trying to describe that shade with hundreds of words in a text prompt.
Which might be clunky or ambiguous.
Yeah.
So that ability to navigate the conceptual map just by combining latent noise vectors.
Yeah.
That's a huge step for controllable generation.
Absolutely. Fine-grained conceptual control.
But hang on, the researchers didn't just stop there, did they? Manipulating the state, that's only half the story in this paper.
Not at all. They pivoted from manipulating the content, which is the state,
Right.
to manipulating the mechanism that controls the state.
Ah, okay. Getting deeper into the machine's workings.
And that transition brings us to their second major contribution, tackling what they call structural noise.
Structural noise, what is that?
So standard RWKV, it uses a fixed set of parameters, often called WKV parameters, weight, key, value.
Okay.
These parameters essentially govern the knowledge compression, how past information gets aggregated and how it decays during that recurrent step.
And these are usually static, fixed after training.
Traditionally, yes. This static set of weights, it's always applied the same way, regardless of the specific prompt or context the model is seeing now.
And the researchers argue that's a problem.
They argue the static nature is inherently suboptimal. It acts like a kind of fixed weighting bias, or what they term structural noise.
Is there an analogy in transformers?
Yeah, they draw an analogy to attention noise in standard transformers. That's when the fixed attention mechanism struggles because the context demands something unusual or non-local that the fixed pattern isn't good at.
Okay, so a fixed mechanism causing issues. Here's where it gets really interesting then. What's the radical proposal?
The proposal is, well, pretty radical. Don't just accept the structural noise. Mitigate it by dynamically generating the recurrence parameters themselves.
Whoa! Generating the parameters like the core WKV matrices, WR-KWV.
Exactly those.
But wait a second, they're using a diffusion transformer, which we know can be computationally heavy,
Right.
to generate the parameters for the RWKV block, which is supposed to be the fast component. Doesn't that just, shift the bottleneck? Are we losing the efficiency?
That's a really critical question. Efficiency is key here.
Yeah.
And the answer lies in the context of how it's used.
How so?
The DIT, the diffusion model, it doesn't run token by token alongside the RWKV. That would be slow.
Okay, so it's not constant generation.
No, it processes a variable length global context. Think the high-level prompt or maybe the first chunk of a sequence. It looks at the big picture to track global features.
And then it generates the parameters. That computational overhead gets spread out.
It gets amortized over all the subsequent tokens that the recurrent block processes lightning fast using those tailored parameters.
I see. So it's like a one-time or occasional configuration step.
Yeah.
A setup cost that pays off over the fast generation part.
Yeah.
It configures the operational laws of the fast module.
That's a great way to put it. Operational laws. This parallel DIT dynamically generates a set of context-specific parameters. Let's call them TEAT again.
Okay.
But crucially, these generated parameters, they don't just completely replace the fixed ones learned during training.
Why not? Wouldn't that be maximum adaptivity?
Maybe too much adaptivity could lead to instability. Instead, they fuse them.
Fuse them how?
They're blended with the stable, statically trained base parameters,
Yeah.
theta static through interpolation. The final parameters used, theta WKV final, or a weighted mix.
So like theta WKV final alpha,
Well,
so
it's
that
sort
is
of-
plus 1 alpha theta, something like that.
Exactly that equation, where alpha is itself a learnable hyperparameter. It learns how much to trust the static versus the generated parameters for a given situation.
Okay, let me see if I got the high-level concept. We're blending the stable core knowledge baked into the static weights
Yep, the long-term learning.
with this temporary, highly context-specific knowledge coming from the dynamically generated weights.
Right.
And alpha is like a volume knob, deciding how much dynamic modulation we actually need for this specific input.
That is precisely the conceptual summary. It gives you a principled, controlled way to counteract that fixed structural noise.
Meaning the model can actually dynamically configure its own operational rules based on the global context it sees. The recurrence mechanism itself becomes adaptive.
That's the goal, a self-configuring recurrent engine.
A globally informed parallel module, the DIT, dynamically setting the rules for a local efficient serial module, the RWKV block.
That sounds incredibly complex as a hybrid architecture.
It is complex.
Yes.
You've got a diffusion model generating parameters, feeding into a language model that uses those parameters to generate text. How on earth do you train something like that without it just falling apart?
Yeah, that takes us right into segment 4, multi-objective training. And you're right, training the system means wrestling with a multi-objective loss function, no objective total.
Multi-objective, meaning you're trying to satisfy conflicting goals.
Often, yes. It's a major engineering hurdle because you are balancing two fundamentally different kinds of objectives simultaneously.
Okay, what are the two main objectives here?
Well, first you've got the standard language modeling task. Let's call it math call. That's just your basic next token prediction loss. The model has to get good at predicting the next word accurately.
Standard stuff for an LLM. What's the second objective?
The second one is the parameter generation task. The math call prem, that's the diffusion loss. It forces the DIT part to get good at accurately modeling the distribution of useful parameters and reducing that noise effectively to generate them.
And why is balancing those two often so hard? Why are they potentially adversarial?
Well, think about it. The language modeling part, math call LMM, It thrives on stable, predictable weights to make good predictions.
Consistency helps prediction.
Right. But the parameter diffusion part, math call par, is inherently stochastic. It's generative. It's dealing with noise reduction and probability distributions.
So one wants stability, the other embraces variability.
Exactly. Trying to jointly optimize these two, where one focuses on precision, the prediction, and the other focuses on distribution modeling, the generation, that's where a lot of hybrid models can fail. You can get training instability, or one part overwrites the learning of the other, catastrophic forgetting.
So did they manage to stabilize it?
This is where the paper shows some real scholarly rigor, I think. They demonstrated the viability of this joint optimization. Their results, they included training curves.
The loss curves in Figure 3.
That's the one. They show the training loss for this whole dynamic parameter synthesis architecture. And it shows stable, consistent decreases over time for both losses. Math colorome goes down, and mass colorome goes down.
Okay, so it is possible to train this beast. They proved the joint optimization works.
Exactly. It confirms this complex joint paradigm is viable and seems highly effective, at least in their setup.
So connecting this success back to the bigger picture, what does this work really pioneer?
Well, it feels like a really solid proof of concept for combining, traditional token-wise autoregression.
The standard model generating token by token.
Right. Combining that with a genuinely novel concept-wise autoregression.
Concept-wise, how so?
Through the probabilistic generation of the state, which represents a concept or persona, and the parameters, which represent the operational mode, it's like the model is reasoning at a higher level of abstraction than just the next word, and that leads you directly to the highest level implication, I think, by modeling and controlling both the internal state and the recurrence parameters probabilistically.
Using these diffusion methods.
Yes. These models start to look less like static predictors and more like building blocks for truly controllable and adaptive world models.
World models.
Yeah.
Systems that build internal representations of how things work.
Kind of. Systems that can continuously adapt not just their internal knowledge representations, the state, but critically, their very operational mechanisms, the parameters, based on the environment or context they encounter.
Making them fundamentally more capable, potentially, than models stuck with fixed weights forever.
That's the potential. And it definitely raises some important questions for where this research goes next.
Okay, let's try to quickly recap the key takeaways for you, the listener. First, we learned the internal state of modern RNNs, like RWKV, isn't just passive memory.
No, it's a highly structured manifold. DreamState proved that with the TSNE plots showing those distinct clusters for different expert personas.
Right. Second, we saw we can get really fine-grained conceptual control by interpolating these latent states. Remember the desert and perseverance story blend.
A very convincing demonstration of control.
And finally, we saw the successful proof of concept for fighting structural noise. Dynamically generating the recurrence parameters using that parallel diffusion transformer.
Blending the stable static weights with context-specific generated ones.
Exactly. It makes the model itself adaptive.
So my final thought for you to maybe mull over, building right on that dynamic parameter idea.
Okay, leave us with something provocative.
Well, if we can successfully change the core laws, the actual recurrence parameters of a language model based on the context it sees, what are the real limits of adaptivity here? Could future large language models eventually maybe abandon these huge fixed static weight matrices entirely?
In favor of what?
In favor of systems that continuously synthesize their own operational components, their parameters, based entirely on the input stream they're processing? Are we heading towards truly self-configuring AI?
A fascinating and maybe slightly daunting thought. Definitely something to ponder as we watch this space.
Indeed.
Until next time, keep diving deep into the research.
Today, we're going to dive into a really fascinating new paper. And it's not just about making AI bigger or faster. Nope. This is about a framework called DreamState, which is all about looking inside an AI's mind to unlock a whole new level of control and adaptability. We're talking about AI that might need way less training data or could be corrected without all that expensive fine-tuning. So, the research here really kicks off with one central mind-bending question. What if an AI could do more than just process information? What if it could fundamentally adapt its own internal thought processes for any given task? You see, that's the leap from a static tool to a truly dynamic intelligence, and it's exactly what this paper starts to unpack. Now, to really get why this is such a big deal, we've got to understand a core conflict that's kind of at the heart of all modern AI development. It's this classic battle between raw brute force power and just, practical efficiency. So on one side, you've got the heavyweights, transformers. This is the architecture behind models like GPT-4. They have incredible raw power, for sure, but they get super expensive to run and slow down to a crawl when you give them long chunks of text. And on the other side, you have recurrent neural networks, or RNNs. You can think of these as the sprinters. They're incredibly fast and memory efficient. The big challenge has always been, how do we bridge that gap? How do we get the speed of an RNN with the power of a transformer? Well, the secret sauce of an RNN is something called its state. The best way to think about it is as the AI's short-term memory, or maybe like a mental scratch pad. It's a compact summary of everything it's processed so far. Now, for a long, long time, this state was pretty much treated like a black box, just a jumble of numbers we couldn't really make sense of. But the researchers behind DreamState asked a critical question. What if that jumble is actually a map? And that brings us to the first huge contribution of this work. They set out to prove that this internal state isn't just random chaos, not at all. Instead, it's a highly structured space, a kind of internal map of concepts that we can actually chart and navigate. So what is it? Is it just noise, or is it a map? The researchers decided to try and visualize this internal world to find out for sure. And the answer they found, well, it's a total game changer for how we think about controlling AI behavior. And here it is. This, right here, is the map. What you're looking at is a special kind of visualization, a TSNE plot. Now, don't worry about the name. Just think of it as a tool that takes the incredibly complex, high-dimensional data of the AI's internal state and just flattens it into a 2D picture we can actually understand. Each little dot represents the AI's mental state after a specific prompt. And what's absolutely amazing is that they form these distinct clusters. You can literally see a neighborhood for states related to writing code, another one over here for creative writing, and more for things like logic. This is the proof. The AI's mind has a geography. Okay, so if we have a map, can we actually choose the destination? Well, this table shows that the answer is a resounding yes. The baseline model completely failed when it was prompted about perseverance. Using DreamState to generate a storyteller state got the style right, but it missed the topic. But this is where it gets brilliant. By interpolating, which is basically a fancy way of saying they mathematically blended two different mental states, they combined the state for perseverance with one for a story about a desert. And the result? A perfect metaphorical story. This proves we can get direct, fine-grained control over the concepts the AI is thinking about. All right, so we can edit the AI's mindset. That is breakthrough number one, and it's a big one. But even if you can choose the AI's state of mind, what about the fundamental rules it uses to think in the first place? The paper now pivots to tackle an even deeper limitation, the fixed, static rules that govern how an AI operates. And this analogy is just perfect. Most AIs are trained with a fixed set of parameters. These are their core operational rules. It really is like a master chef who's forced to use the exact same recipe and the exact same oven temperature, whether they're trying to bake a delicate cake or sear a steak. I mean, obviously, a single static approach is never going to be optimal for every different situation. The paper actually gives this problem a specific name, structural noise. From a more academic view, this isn't just random static, right? It's a fundamental inefficiency caused by the mismatch between the model's fixed universal rules and the optimal rules it would need for a very specific context. It's like a built-in handicap. And this quote from the source just puts it perfectly. This structural noise, it really hurts the model's ability to focus on what's most important in any given situation. But the paper's authors don't just identify the problem. They propose a really radical way to cancel it out. And this, for me, brings us to the second and arguably even more profound breakthrough. What if, instead of being stuck with a fixed set of rules, the AI could analyze the context and just rewrite its own operational parameters on the fly? Now, this diagram shows their brilliant solution. It's a hybrid architecture. So on one side, you have the main RNN model, the workhorse that's generating text step by step. But here's the key. Running in parallel, there's a second module, a type of AI called a diffusion model. Its only job is to look at the entire prompt, understand the context, and then generate a brand new, custom-built set of operating rules. It then feeds these perfect, tailor-made rules to the main AI to use for that specific task. Let's break that down. It's pretty simple. Step 1, the diffusion module analyzes the global context of whatever you've asked it to do. Step 2, based on that analysis, it generates a new set of custom parameters, or rules. And step 3, these new dynamic rules are fused with the model's static base rules to execute the task with way more precision. It's literally an AI that tunes itself. And you might be thinking, okay, sounds cool in theory, but does it actually work? Well, this chart is the proof. In machine learning, a loss curve basically shows how many mistakes the model is making during training. A steadily decreasing curve like this one, that's the gold standard. It means the model is learning effectively. And the fact that this curve is so smooth is honestly remarkable. It proves you can stably train a single AI to do two very complex things at once. Learn to perform a task and at the same time learn to generate its own optimal rules for that task. So, let's pull these two revolutionary ideas together, a mappable mind and an adaptive engine, and really think about what they mean for the future of artificial intelligence. So if you remember anything from this, here are the two crucial takeaways. First, we now have evidence that an AI's internal state isn't a black box. It's a structured, meaningful, and most importantly, an editable space. We can literally guide its thought process. And second, we have a working proof of concept for an AI that adapts its own fundamental operating system for the task at hand. It's moving from a static tool to a dynamic, context-aware reasoner. And that leaves us with a final and pretty profound question to think about. The next frontier for AI may not be just about accumulating more knowledge from the internet. It might be about building systems that can fundamentally change their method of reasoning, of problem solving, and creation from one moment to the next. So what happens when an AI can change not just what it knows, but how it knows? That's the future this paper is pointing towards.